let's get started. Hello, everyone. I'm Junchen, CS professor at the University of Chicago. And today, I'm happy to join with my student Yihua here and Zhou from Mooncake Labs to share with you what we believe is the key to unlock the future of LLM applications. And this is based on a decade-long research in building large-scale AI systems. First of all, generally, LLMs have two challenges. First of all, LLM training. Hundreds of millions of dollars have been spent on this, and only a small number of companies are really into training new LLM models. But in contrast, millions of applications are using LLMs to run LLM inference. Okay? Microsoft, for example, estimate that there will be 750 million applications running LLM inference in the next year. And many industry leaders believe that every single application or service will be running LLM very soon. So that's why our primary goal in this line of research and development is to create a better service for LLM inference, in particular, long context LLM inference. Now, why long context? First of all, long context presents the biggest opportunities in the next few years. For example, there have been a lot of talking about long context and even infinite context windows these days. With long context, for example, you can feed hundreds of books to your LLM and immediately start asking it detailed questions about these books. With long context LLM inference, you can also dump a big code repository into your LLM and immediately starting asking it to create new test cases or even add new features to the code base. With long context LLM inference, you can also upload hours of videos from your smartphone to your LLM and asking it to summarize memorable moments from this video. Now, the list of exciting applications enabled by long context LLM inference goes on and on. So that's why long context inference capability is believed to be the key by many people as the key enabler for the next wave of LLM innovations and applications. But there's always a but. Long context inference also presents the biggest challenges in terms of the delay to serve this context, in terms of the amount of resource you need to process this context, and also the quality will suffer because if you let the model only read the context once, the model may not be able to to find all the useful information in it. Okay? So here I use the two figures to show you the increase of delay and also the increase of amount of resources you need to process long context. With longer context, the model needs longer time to process the context, and also the amount of resource you need to process the long context grow super linearly with the length of context. And this is true even with all these sparsity-based optimizations. Okay? So just to give you context, just give you some perspective, a large code repository, the length of the large code repository will be something like a Kubernetes code base will be 2 million tokens. A long book, a 200-page book, will be about 250K tokens. And about a 1-hour video will contain at least 360,000 tokens. And all these token numbers are way towards the right of these figures. Okay? So clearly, there's a big problem. Now, to unleash the potential of long context inference, what we need is a better system. A better system that can serve long context inference with lower delay and lower cost and at very high quality as well. Okay? And we believe we have an answer to that, and that's driven by our decade-long research in large-scale AI systems, building large-scale AI systems. The key insight here is you need a better abstraction for the long context data. Traditionally, long context data will be used as part of the input, so-called in-context learning. The context will be viewed as part of the input tokens. Now, that's why the model needs a lot of time to process it. Now, that's very slow. And on the other hand, so-called fine-tuning models, LLM fine-tuning, embeds those new contexts or new knowledge in the model's weights. But it takes a lot of time to fine-tune the models in the first place. And these fine-tunings usually takes hours to tens of hours to even several days, and sometimes you don't get it right the first time. Our insight is that the abstraction for long context data should not be the tokens, or should not be the model weights. It should be the KV cache. So what is KV cache? KV cache is the internal understanding of the of the large language model on the long context data. Okay? So you feed the long context data to the model once, and the model can create an internal understanding, which is the KV cache. So that's why if you use KV cache as a representation of the long context, the model can use it and understand it directly. And that's the high-level reason why we focused on long context, why we focused on KV cache as the abstraction for long context service. And LMCache is basically this open source project we have that's inspired by this new abstraction called KV cache. And it's a highly optimized implementation for managing and serving long context data in the form of KV caches. Because KV cache already captures the model's internal understanding of the long context data, serving the long context inference with KV cache can massively speed up the inference, and also it avoids a lot of repeated computation because if the context is used again and again and looked at by the model itself. And also, because you can change the content in the KV cache, you have a good chance to improve the quality, which is not covered in this slide. And all these benefits can happen without changing the model and the context, okay, or the prompt. So it's totally transparent to the applications running on top of it. Now, enough talking about the abstraction ideas of our LMCache. So let's just quickly look at the speed up. Right? So compared to VRM, probably a lot of you guys have heard about. It's a widely used open source project in industry for its superior performance over alternatives such as TGI or Ollama. But compared to VRM, LMCache can still reduce the response delay, the so-called time to first token, by 10x in popular applications such as multi-run QA, retrieval augmented generation, or RAG. Okay? Now, again, I want to emphasize that LMCache is a system on top of existing serving engines. So it's actually built on top of VRM. So if you use VRM, you can use LMCache directly. And not just serving LLM inference faster, it can also reduce the cost compared to, I mean, if we want to achieve the same serving throughput on the same model, here we compare to our serving cost with AWS, AWS on-demand service, or any scale these popular services. The cost can be 5 to 10x cheaper depending on the characteristics of the workload. So before I hand over to the student and collaborators to show you the demos, I want to quickly go over the architecture of this system. There is a request router at the top that handles all the requests and map that to serving pods. And each serving pod runs a state-of-the-art VRM serving systems. We collaborate with VRM so that the serving pods can run the latest VRM version. And behind each VRM, there's a front-end server of LMCache that handles the interaction with VRM and also maps the KV cache back to the backend. And the backend will be an efficient storage system of KV cache on top of heterogeneous storage hardware. So a very quick walkthrough of the process of storing KV cache looks like this. A request comes in, the router maps that to one of the serving pods. The serving pods runs VRM to create a KV cache. Now, this is the first time you see this context, you have to run the inference once. But when the VRM creates the KV cache internally, the VRM will tell our backend, our front end, here is a KV cache, a new KV cache. The first time I see a new context, where to store the KV cache. And front end will ask a KV cache manager to decide which backend server or which backend servers to store the KV cache. In this case, it can be distributed, stored in different locations. So that's storing KV cache. What about retrieving KV cache? Now, if the next time a request with a very similar context coming in again, the VRM will ask our front-end server, have you seen this context? Have you do we have the KV cache of this context in the first place? The front-end server will ask the KV cache manager to get the location of the stored KV cache, and they can be merged together. So this all sounds quite familiar with you if you know a little bit about KV cache related research. But what's new here is that the KV cache is not stored as its original big tensor format. We speed it up by compressing KV cache into bit stream so that KV cache can be flown easily and quickly across different nodes, across different pods. And more than just compressing KV cache, we also allow KV cache to be composed dynamically in a way that if you have input with multiple contexts in it at the same time, the KV cache, let's say if you have seen these context documents separately before, you can combine the KV cache in a dynamic way so that you don't have to reread the whole documents over and over again. Okay, so these are our two, I just highlight these two optimizations. There are a lot of engineering optimizations behind the LMCache system, but I think I've highlighted two optimizations, and there are many more. Feel free to check out the code repository. And now I'm handing the stage to Yihua to give you guys a quick demo of the whole thing, the real thing. Please.
Cool. Let me try to. I think I need to maybe stop.
Oh, I see. Cool.
Okay, cool. So yeah, so what we have here is we are having some Lambda servers running with A6000 and deploying some VRM and VRM with LMCache. So basically, what we are currently doing is we have a LMCache with VRM deployed on a Kubernetes environment. So if you do this kubectl get pods, you will see here is LMCache VRM deployment, and also here as well. If we do the kubectl get pods, we are seeing there's a standard VRM deployed here. And based on this deployment, based on the serving engine deployment, we are running some very simple RAG application on the front end. So let me open up this one. So on the left-hand side here is VRM engine plus LMCache with KV blending feature. And on the right-hand side, there's a standard VRM engine. And what we're running here is basically there's a very simple RAG application, which is configured to retrieve 5 trunks. And in the total, there is 25,000 tokens. So this is a long context example of a long context, although it's not that long. And the documents, the database is about it contains a list of documents and man pages about a command line tool called FMPeg. And right now, let me go to ask it a few questions. And so, for example, we can ask like, what's FMPeg? So describe what. Okay, well, FMPeg in 10 words. Let me copy it to here. And OK, let's feel the speed. OK, on the left-hand side, so the LMCache is generating the answer with just time to first token of 1.71 seconds. And on the right-hand side, the original VRM, it takes 5.40 seconds to prefill, to process this 25K long context and generate the results. And let me maybe just ask another question. So say, for example, how to specify input file using FFmpeg. Pasting here. OK, it's running. Like you can see, the left-hand side, it almost immediately start generating the response. But on the right-hand side, the VRM, the original VRM, still need a couple of times, need some time to pre-process the retrieved chunks. So to conclude, like LMCache not only can not only reduce the time to first token, reduce this response delay. Also, it saves the GPU cycles when pre-processing those long contexts. And yeah, that's basically a quick demo of the LMCache. And let me hand the floor to Zhou here.
OK, cool. OK, cool, yeah. Thanks for all the work. Thanks for all the great demo. And let's actually see, like, we talked about a lot about the RAGs already. But let's actually feel a RAG in production. I guess like many of you probably already like seen RAGs, but like let's feel an actual RAG in production. So this is RAG. Oh. Is it playing? How to play it from? OK, yeah. So this is like a chat app we took from one of the great Postgres companies, and then we asked the question like how to do analytics in Postgres. We didn't slow it down at all, but you can see like there's like a heartbreaking like 20-second wait until like it actually starts generating question like the answer. The actual answer generating is pretty good. Like we know the companies we work with, like the RAG application builders, to make it like try different retrieval techniques or improve the quality. But like there's hitting a wall. Like there's no way to get the time to first token down. And I'm myself a database person, so the first thing like we try always in this kind of application is like, OK, so let's make database better. So we actually spend time to build like a state-of-the-art vector database. And then when we start handing them into like the application developers' hands, we start to realize it actually don't matter at all. Like when looking at the whole like time spent across the RAG application, the retrieval comparing to like the re-ranking and generation using LLM, it does not matter at all. So we're not actually optimizing anything here. Then we'll start looking at, OK, what's the actual solution? Well, that's when I found the LMCache project. I think, OK, maybe it's not a data problem at all. So LMCache will actually shrink the time to first token by shrink the pre-filling time of LLMs. Great. That's the actual solution. Well, but wait a second. I soon start to learn like each LMCache is actually on the magnitude of like hundreds of megabytes or 2 gigabytes. So we are actually still having another data problem, and the actual bigger data problem, since like what we store are actually bigger. We need to manage the KV cache. Cool. So let's actually try to rebuild a better RAG or better general application. Hopefully, most of you should be familiar with like the classic RAG. If you're not, like just please read it. So the classic RAG works by you have documents and you have data. You store them into like a vector database, embedding them, and then at query time, people will query the vector database to retrieve the relevant information, and then like you will throw the context and prompts as like natural language into like LLM, and then the LLM will be generating the response. OK, let's see like how can we actually utilize LMCache and then put that into this whole diagram. The hope is like apps will be able to manage the KV cache just as it's like managing all the vectors, all the embeddings in the vector database. So instead of just storing the data in vector database, we'll start to pre-process them. So we can like generate a lot of like, for the probably the more useful longer context, pre-process them with like LLM, and then generate and store those states in LMCache. So in query time, like we don't, if you find something already in the LMCache, you no longer need to feed the whole like context and prompt in natural language. You directly serve the cache content, which will be much faster. But what do you actually expect the application builder to actually manage, in addition to managing a vector database, also start to manage a KV cache? What if we can provide an end-to-end solution? So this is like what Mooncake is trying to do. We are trying to build a modern data lake. I guess for people like in the data community, essentially data lake is like you have object store. People start to throw like all kinds of different like arbitrary data into it, and then build things on top of that to like get value from it. So what would that look like in this scenario? So people would just like store data as like data lake tables. Those will just stored on object stores. And then on top of that, instead of like just moving data into a vector database and index them, we directly build some vector indexes on the object store directly. And then, in addition, things like the data lake already have a lot of the background processes to do optimizations, to do compaction. It's very nature to also add something to just pre-process the documents and then to generate those LLM states. And the LLM state can also be just stored in the object store. Although they're pretty big, but like storing an object store is cheap enough. And then for like the user application at query time, you just query the whole data lake and do the retrieval, and it will automatically like either retrieve the context or retrieve the actual LLM cache and serve in the optimal format to LLM to make it faster. Yeah, this is essentially what we saw like the RAG evolution over what's hard to believe it's already 2 years. So at the start, everyone's having like in-memory vector databases. It's pretty fast, especially the vector search itself is like extremely fast. But the cost at scale was like crazy. People would spend like 10 times or 100 times what they spend on regular databases than they spend on like in-memory vector databases. Then people start to like when they have like bigger workloads or they realize like retrieval does not matter as much, they start to use like object store-based vector databases. That's like LansDB or protobuffer. So the cost was much, much better, since like you no longer pay the in-memory. It's like stateless, everything stored on object store. But the performance, like even the retrieval part, is getting slower. And then now we see like, what if we actually put like VectorDB and LMCache both in object store? The cost was still great. You store a little more documents, but it's on object store, so cost is not the highest priority. And then the performance is actually better, and even better than the previous in-memory implementations. Okay, let's actually try to fill it in a video demo. So we are extending the Kiwi cache to actually like, we store the Kiwi cache inside object stores, and then on the other side, like it's just feeding from local in-memory databases. Let's see the performance. So you can see that like we can serve from object store even faster than serving from local in-memory state by storing the LM cache together with your data. Cool.
Let me just quickly summarize. First of all, LMCache, this project in collaboration with Mooncake Lab, we strive to make this thing as easy to use and deploy as possible for our users, including container images, including library-based deployment, and also on cloud. And this project is not, doesn't exist in a vacuum. We collaborate with both open source communities and also industry design partners, and we closely work with open source communities to leverage their latest serving engines to improve our basic serving performance, and also to be able to run different models on different hardware. Okay, so that's the power of open source community. And as we get more industry adopters, we're always looking for more use cases from you guys. If you feel like you want to contribute or you have a good use case for long context LLM serving, please reach out to us, okay? Or scan the QR code down there. So just want to quickly summarize the whole thing. First of all, like I said, LLM inference, in particular long context inference, is going to be very important, present the biggest opportunity, but also it creates the biggest system challenges. And to unleash the potential of long context inference, we need an efficient system. And in our belief, the best system to serve long context inference will be the system that can manage KV cache efficiently. Okay? That's the key to the success. And LMCache is this one instance. We built this to combine by combining latest VLM serving engine and the latest KV cache research and technologies. And Mooncake Labs create this enabler for us to make this trade-off. So what is trade-off here? The trade-off is you need to store a lot of KV cache in big data format. And those KV cache doesn't have to exist in your CPU memory or local disk. It can store on S3. And Mooncake Lab enables that. I think that creates a whole ecosystem of KV. I mean, creates the sort of the initial version of the whole ecosystem for KV cache optimization. That's the vision. Okay. So thanks for tuning in, and we're happy to take any questions now.
Hi, great presentation. Quick question. Can you not use an object store in cluster, like, for example, min.io or a Redis blob store?
Oh, good question. Yeah, absolutely. Like, there's many ways to store these KV caches, but so you can store it locally, or even just store it in memory, or even in GPU memory. But like, but they are very large. So in order to like efficiently like store them, you want to store it on something like cheap enough, and ideally like more cloud native. You want to like actually separate the storage and the compute, so you can like serve it on any compute instance without need to like worry about do you actually have the cache locally.
Right. Thanks.
Hello. I have a question in terms of the infrastructure you put. So you have the LMCache to cache your vector database. Am I understand correctly?
Sort of, yes. You have to store KV cache somewhere, and database will be the natural choice to store them, yes. To index them.
So if I catch the slide correctly, you store the preprocessed LLM state on the LLM cache. So what exactly is the preprocessed LLM state?
So I'm asking how to get, how the LLM create the KV cache in the first place? Is that a question?
No. So you get so in the diagram you put a preprocessed LLM state on the to store in the LLM cache. So I'm not sure what sees the preprocessed LLM cache is. Yeah, preprocessed LLM state.
Yeah. So initially, you just store like throwing data into these like tables, and then you need to somehow like generate the LLM states. Then later you can just serve them. So this is the pre-process. Essentially, in the background, you want to start like use LLM, ask it like what would be the LLM, what would be your state if I prefill with this document, and then you save them. Then later, when you actually need to use it, you can directly use the pre-processed LLM state.
Thank you.
Hi. You mentioned earlier around if you've already processed some documents, you got them in there, you can add new documents without pre-processing the old documents again. But how do you handle things like if you want to handle multiple versions of a document that have, like, for example, the Kubernetes documents for version 1.2 and 1.3, like just having different versions of the similar document? And in addition, how do you subtract documents back out of there? Are they stored as separate kind of bodies in there, so you can say remove that document?
I'm so glad you asked that, because so basically, the KV cache is a function of the text and also the model, right? So you ask about what if the text changes slightly, incrementally, right? If you change the text incrementally, the part of the text that's not changed by that incremental change can still hold the KV cache. Now, again, but the next time you use the KV cache, you have to update its attention matrix slightly. Now, you don't have to change the attention matrix completely, because only our key observation in this line of research is not every pair of tokens have important attentions between them. Okay, so if you change things incrementally, the KV cache of those changed tokens will definitely be changed. But the remaining tokens don't have to be changed a lot at all because only a few tokens need to be updated. So that's the idea. So just slightly extend your question a little bit. Like I said, KV cache depends on both text and the model. The model can change as well, right? Maybe you fine-tune the model. What if the KV cache, what about the KV cache? Can it be still reused with, by the new model? That can also be reused. That's just part of things that the LMCache can support as well. But again, if the model is completely changed, or the architecture is changed as well, then the KV cache shape will be different. So that's a different story then. Thank you.
Thank you.
Hi, great talk. I had a question about VLLM has this prefix caching. So does that use something like this under the hood, or what is the difference?
So short answer to you is VRM itself only store KV cache in GPU memory. It does use CPU memory for offloading, but it doesn't hold CPU, in sort of reuse KV cache across inference using CPU memory. So early on, we collaborate with VRM team closely on this because they also realized that KV cache is something you want to hold for a long time. So you definitely need a backend system to store KV cache, not in GPU memory, not just in CPU memory, but also distributed across multiple nodes. So that needs a separate system, and LMCache basically is the open source projects to support that.
Sounds good,
Great,
thanks.
thank you.
One more question I had, in this RAG setup, you would have a lot of documents that you would create LLM cache for. So when you retrieve it, I'm assuming you have some sort of indexing to retrieve only specific cache for that prefix in some way. So how does that work? Do you store them? How do you store them in an S3 bucket, and how do you retrieve?
So is the question how to look up the KV cache store to find the KV cache of the right?
Get specific portions of the KV cache from.
Yeah, essentially, KV cache, you kind of store similar to you store your documents. Essentially, previously you use vector search to retrieve a document. Now you use the vector search to retrieve the corresponding key LMCache entry. So it's kind of the indexing and retrieval part is kind of similar.
Okay, very similar to VectorDB, but instead of
yeah, but everything's on object store.
Sounds cool. Thank you.
Hi, how does this work for structured data like Delta Lake or Iceberg? Can you use this for structured data?
Structured data.
Instead of documents, can I use it against some historical data that we have?
Depending on what's your use case for feeding into the large language model and then to generation. For example, if you actually throw in all the tables or the context itself into LLM, then definitely. But if you actually, for example, you run a query first and then throw it into LLM, then probably you do directly build your traditional RAG against your database.
Right. Well, what would you recommend? You would recommend LLM to generate a query and then query the database, or would you feed the structured data?
Oh yeah, I guess it totally depends on your use case. If the use case is actually for example BI, you actually want insights if you actually want to run SQL, then run SQL against the traditional database is probably better. But if your question are more ambiguous or more you want to ask some more human questions, then just directly feeding everything into LLM might be a good choice.
Yeah, hypothetical scenario, a stock price chart you have, and then you want to block a chart, but a user wants to talk in a natural language and be able to generate that against some historical data that we download from external sources.
Yeah, so if it's plot, it's usually better to have our, or there are several ways. One is you can provide the API for function calling to the LLM. Then this will probably do the best job, and the next best will be how LLMs generate SQL.
Got it. Thank you.
Great.
Hey, last question. I think I had a quick question. Great presentation, by the way. I love the demo. So the cache that you have, right? I was concerned about what is the hit rate of the cache? How often do you have this repetition for context?
How often do you update the KV cache for the context?
Right. Yeah. I mean, or how often do you when you look up the vectors to retrieve your cache? What do you think is is the repetition? How often does your cache get a hit rather than having to compute it all over again? What's the hit rate?
That's a good question. So It really depends on the application that issues the query in the first place. Chat applications will have pretty frequent reuse of KV cache, although the KV cache will be about, it's chat history is not going to be very, very long context. But of course, if you have very long conversations, the context can grow indefinitely. For RAG services, it also depends on whether there are hot items in the database or not, right? So if you have context that, chunks in the database that's queried, but that's being used as the context for many queries, those chunks will be hit very frequently, much more frequently than others. So if you talk about exact time duration between 2 hits of the same chunks, so we run some analysis for our own research papers. So we use traces from Moonshot AI from Microsoft and also I forgot the other company, but they're open source traces. They don't necessarily represent real the most representative workload in real world, but the impression I got was about tens of seconds to several minutes. That's sort of the median. Now, of course, there are situations you reuse the KV cache just within several seconds to hours. What I want to emphasize is traditionally, people think about KV cache to be to be stored in GPU. That only applies when the reuse happens within several seconds, which is not a common case in real world. So that's why you definitely need an extension of the KV cache storage like LMCache.
Got it, for longer durations of retention.
Yes, exactly.
Yeah, thanks.
So I think we're running out of time. Thanks for everyone for tuning in.